Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 12, 2026, about 5 days ago. It introduces a new paradigm called test time tool evolution that allows agents to synthesize, verify, and evolve their own tools during inference instead of relying on fixed libraries. The paper is titled Beyond Static Tools, Test Time Tool Evolution for Scientific Reasoning. And as we'll see shortly, this capability allows the model to achieve state-of-the-art performance on a massive new benchmark of scientific tasks. For those interested in the implementation, the authors have shared their code on GitHub. So, Figure 1 visually breaks down this core difference. On the left, we see the traditional static tool paradigm. Here, tools are pre-built into a fixed library before the model ever sees a problem, meaning the agent can only retrieve what is already there. If a required tool is missing, the system hits a wall, because there is no runtime generation. In contrast, the right side illustrates the new test time tool evolution approach. Instead of a static collection, we have a self-evolving loop, where the model generates new atomic tools on the fly, validates them, and updates its dynamic library in real time. Well, Figure 2 details the architecture that makes this possible, operating in a closed loop. It begins on the left with structured task decomposition, where the problem analyzer breaks a complex query into executable subgoals. From there, the process flows to dynamic tool retrieval, which queries the central registry to see if the necessary tools already exist. If they do, the runtime execution engine on the top right simply runs them to get the final answer. However, if a tool is missing, the generative tool synthesis module creates it on the fly, validates it, and then passes it to atomic tool refinement to be registered for future use. Alright, having seen how the system works, Table 2 presents the main accuracy results across 3 benchmarks: SciBench, SciEvil, and SciEvo. The top section lists the baselines, ranging from basic chain-of-thought prompting to specialized agents like Creator and KTCE. In contrast, the bottom row highlights TTE 0, which consistently outperforms every other method. For instance, on the SciBench dataset, it achieves an accuracy of 0.45, a significant jump over the strongest baseline, KTCE, which sits at 0.37. Similarly, on the new SciEvo benchmark, TTE 0 reaches 0.62, proving that generating tools on demand yields better answers than relying on static libraries. So Table 1 digs deeper into this efficiency by analyzing the tool reuse rate. This metric tracks how often a generated tool is actually used again, which indicates whether the model is building a library of useful primitives or just disposable code. Looking at the bottom row, TTE 0 achieves near-perfect utilization. For example, on the SciEvo dataset in the rightmost section, it hits a reuse rate at 1 of 0.99. This means nearly every tool it created was reused at least once, whereas baselines like Creator often produce tools that are never touched again. Okay. Table 3 evaluates how well the model adapts an existing library to a new field. The setup involves taking a toolset built for materials science and applying it to chemistry on the left and physics on the right. In the bottom row, TTE Adapt achieves the highest accuracy, reaching about 60% for chemistry and 62% for physics. The columns reveal the mechanism. The system effectively prunes irrelevant tools from the source domain, shown by the lower transfer reuse rates, while simultaneously evolving new tools to match the target discipline. Finally, Table 9 places the new SciEvo benchmark in context by comparing it to existing datasets. The top rows show that standard benchmarks like SciBench typically rely on internal reasoning with no tool support at all. The middle section lists frameworks like ToolBench and ChemCrow, which do use tools but restrict them to static APIs or fixed libraries. The bottom row highlights the unique advantage of SciEvo. It is the only dataset designed for dynamic tool evolution, supporting over 900 generated primitives. Wrapping up, 2 takeaways stand out. By synthesizing tools on demand, this method overcomes the rigidity of static libraries and achieves state-of-the-art results. Broadly, this suggests that for AI to truly tackle scientific discovery, agents must evolve from passive users into active creators of their own computational instruments. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.